Physics of the Institute of the first of Theoretical and Computational Physics. So today we are going to dive into the quantum frontier. We have the pleasure of having with us Professor Michalis Skotiniotis, who is a Monica Hart Fellow in our department, the Department of Electromagnetism and Quantum Matter Physics, who is going to talk about how he learned to love quantum theory.
Correct.
Worry about extraordinary gatsby and friends and Einstein. Michalis, thank you very much.
Thank you, Pablo. Thank you all for coming. It's a pleasure to be here. As Pablo said, it's going to be in English. I'll try and speak loudly and slowly. If I go fast, please raise your hand and tell me tranquilo. Right? Okay. Just sometimes I tend to go fast. Okay. So today's talk is going to be about this thing that you may have heard of, called the second quantum revolution. And when I first heard about the second quantum revolution, I stopped and said, well, wait, when was the first one? Did I miss it? So what do people mean by the first quantum revolution? Is things like this. So in 1938, for example, Rabi discovered the nuclear magnetic resonance. This is why we have MRI machines nowadays. Okay, and then 10 years later, we have the transistor, which is a quantum mechanical device, one so to speak. And then actually the first purely quantum mechanical device goes all the way back to 1952, and that's the first atomic clock, okay, from NIST. And then 2 years later, comes up with the first laser, which is the maser, okay? So this is what I would call the first quantum revolution, okay? And there's a nice heuristic way of understanding the difference between the two revolutions. The first one is people trying to make sense about this new physical theory, okay? Like try to build things, okay? Like MRI devices, lasers, clocks, and so on and so forth. And the second revolution is more like a shift in paradigm, and people trying to understand the information theoretic consequences of quantum theory, okay? So what can we do by, what can we process if I assume that I can build computers and communicate using this theory, okay? So this is what the second quantum revolution is about. And I don't know if you noticed, but there's a bit of a hype about it. So here's, for example, a rudimentary search over the last 6 months of news articles in Forbes and the New York Times, and Google announces a breakthrough that will significantly shift, revolutionize quantum computing, that we're going to build a quantum internet. It's going to be amazing, and all these things, okay? There's the famous one, quantum supremacy in certain things. You're not supposed to use that word anymore. So, or breakthroughs in quantum computers and so on and so forth, okay? And in fact, if you are the kind of person that also looks at kind of the stock market or kind of the, where the money goes, you'll notice that it looks like a little bit like a gold rush. And in fact, every Tom, Dick, and Harry is in it. So the BBVA just got a grant with Multiverse, a quantum computing company in Spain, to do like portfolio optimization on quantum computers. Like Caixa is partnering with D-Wave. You have another bank, HSBC, people hiring people for protecting their secrets, okay? You even have car companies like Toyota and BMW investing in quantum computers, okay? My favorite one though to date is Siemens. And this is the exact quote, okay? This is the reason why they got into it. Siemens will work to enable individual solutions for efficient shop floor management. So they're investing in quantum computing to optimize where to put the microphones and the earphones and so on. What is the best way to do that, okay? Essentially, any excuse to get in it, okay? And it's not just companies, it's also governments. This is the latest research from Davos in 2023. So people figured out, okay, how much money are countries spending in quantum technologies? So the projected number is 30 billion, sorry. I won't go into the details. The only number I want to highlight is of the 30 billion, half of it is China, okay? So there's also, let's say, a new kind of a Cold War, because everyone's trying to catch up to the Chinese, who are sending satellites and doing entanglement and building huge quantum optical networks and all these things, okay? But the point is, this is 30 billion, and it's projected that by 2030, this number will go up by an order of magnitude. So it will be 300, billion, okay? Since we are in Spain, I also thought I'd tell you a little bit about what happens in Spain, just so you know. So for example, I don't know if you've heard, but there's the multiverse quantum computing, which just recently got 10 million euros, okay, to do research in quantum computing. Okay, there's the first quantum computer in the European Union is going to be installed here in Spain. Actually, it's going to be in the Barcelona Supercomputing Center, okay? And then it turns out that people in Galicia decided they also want a quantum computer, okay? And then IBM also decided it's going to partner with the Basques, and they will also build a quantum computer. So from 0 we go to 3 now, okay, in Spain. And then there's, of course, other spin-off technologies like random number generators. This is a company that comes out of ICFO, out of Morgan Mitchell's group. Okay, they are partnering up with a company that deals with slot machines and things like this, okay? I said about this one. And then, just so you know, sorry, I go back. So when I arrived in Spain in 2016, the number of companies that were doing quantum were 0. 0. 7 years later, there's 14, okay? And this is most of them that I found. Actually, I'm kind of sad because the person in charge of the quantum division in this company and the person who started this company, I actually taught them quantum theory. So, and they make more money than me now, so, okay? There you go. So the point is that it's a technology, okay, there's a big hype. Some of it is a bit overblown, okay? Most of these companies in 5 years' time, they're not going to be here, okay? But some of them will, okay? And then if you want to do, let's say, research nowadays in this kind of field, you can stay in academia, but there's also opportunities in these companies that are looking for motivated PhD students. You can do research projects there, okay? So there's a lot of things happening in Spain that you can follow. Okay, so finally, let me tell you also the thing. If you want to stay in academia, then you need to know that the main funding source in academia comes from the EU, and the EU has this thing called the quantum flagship. Essentially, the EU funds 4 major areas of development. One of them is in quantum technologies, okay? And they've identified 4 directions in quantum technologies where funding goes. And I've listed them from most money to least money, okay? So most money goes in quantum computing. That's building quantum computers in different architectures and so on and so forth. Then there's quantum simulators, things that are not quite quantum computers. They are purposely built to do one thing or simulate another system, okay? And these are, for example, say monitoring chemical reactions or doing some sort of biology simulation or such things and so on. Then there's quantum communication, things like cryptography, sending messages down optical fibers and so on. And the one that gets the least amount of money, and hint, this is where I work, so I get the least amount of money, is quantum sensing and metrology, like measuring things, okay? So here's an outline of my talk. Essentially my goal in this talk is to basically tell you, okay, why there's this hype, why some of this hype is well justified, and because it's me, I'll try and do it it's going to be a bit of a selfish talk because I have to talk about what I do. So I'm going to tell you from my point of view why you should do quantum theory, okay, or quantum information theory. Okay, so I thought that we start first of all very simply because I don't know if people know the formalism. So this expression here, it from bit, is a very famous expression by John Wheeler, okay? So you will hear a lot when you see talks about quantum things, people talk about qubits, okay? So what is a qubit? Okay, but before we talk about qubits, let me first of all, this is an important thing from a personal point of view, okay? I draw a line distinguishing things that are called quantum physics and things that are called quantum theory, okay? This is quantum physics. If you learn quantum theory in a physics department, these are the sort of things that you're going to hear about, okay? So things like to each physical system there corresponds a wave function which contains all the information that you need to know about the physical system, that measurements of physical quantities correspond to Hermitian operators, that we have a Schrodinger equation and things like that, okay? Now, this is all well and good. As far as I'm concerned, what you need to learn is this, okay? And quantum theory is a mathematical theory in full meaning of the term, okay? In the sense that it has 3 axioms. The first axiom tells you what are the objects of interest of the theory. The objects of interest are these things called density matrices, positive operators, okay, with bounded trace. The second axiom tells you how to combine objects of interest, okay? In quantum theory, we do this by something called the tensor product, just a way of putting things together. And the third axiom tells you how to go from one object to the other in the theory, okay? And the most general way to do this is by something called a linear, completely positive trace, non-increasing map, okay? What does it mean? It means this is just an object that takes matrices to matrices, and this object satisfies 3 properties. The first one is linearity, okay? So this is just by definition, this is what linearity is, okay? The second one is something called complete positivity. It means that if I have if you want to think of it in physics terms, if I have two subsystems and I do something on this system and nothing on the other, the result should be something physical, okay? So this is captured by this complete positivity condition here, okay? And the last thing is trace non-increasing. This essentially means that the probabilities have to sum up to 1, okay? You cannot do something and then the probabilities are more than 1, okay? That's it, okay? So I say it again, if I had to teach this course, this is what I would teach you, okay? And I stress that I dare anyone to find here a dot or a crossed T or an I that has anything to do with physics. Nothing, okay? Nothing with physics, okay? What is quantum physics? Quantum physics is when physicists come and say, this object here, and they draw a mental arrow and they say, this object describes the mechanical properties of a system. Then you have quantum mechanics. Or when they draw an arrow from here and they say, this object describes the optical properties of a system. And then you have quantum optics. Or when they draw a mental arrow and they say, this describes the electromagnetic properties. And then you have quantum electrodynamics, okay? So all these things, quantum mechanics, quantum optics, is just this formula. That's it. Okay, so just so I get you more familiarized, because you're going to see these objects throughout the talk. Here's, for example, what the Schrodinger equation looks like in this mathematical formalism. The Schrodinger equation is just this thing here. You give me a state or a density matrix, and I apply on either side of it a unitary operator. That's a matrix such that when I take U and its complex conjugate transpose, I get the identity. If you want to think of it more physically, this matrix here is generated by exponentiating the Hamiltonian of the system, okay? That's the Hamiltonian that appears in the Schrodinger equation. Okay, the measurement process, I can describe it by something called a quantum channel. That is, these things here are projectors. They are matrices that have strictly positive or 0 eigenvalues. They are orthogonal, and when I sum them, I get the identity, okay? Probability distributions, the results of measurement outcomes, you can describe them by something called a quantum to classical channel, something that takes a quantum system and spews out a number between 0 and 1, okay? And the collapse of the wave function is just an update rule. And you say, or a coarse graining. I have this map, and then I get information about K, and I update my state of knowledge to this, okay? That's it. There you go, all of quantum mechanics, 2 slides. Okay, fantastic. So, it is precisely the fact that people decided, or at some point throughout quantum theory, we were lucky enough to get a couple of mathematicians and a couple of computer scientists interested in the theory. Okay, so they took quantum physics out of the drawers of all these people who were arguing about, but Einstein is right, no Bohr is right, no Einstein is right, no Bell is right. So this is what physicists did, and then they basically took it and said, okay, what can we do with this thing? Okay? So for example, the invention of quantum cryptography, these 2 people here are not physicists. They're computer scientists. Teleportation, aside from the last 2 people here, these people here are not physicists. Okay? 2 are computer scientists and 2 are mathematicians. This factoring algorithm that you know about, that quantum computers can factor numbers better, okay, it was invented by a mathematician. He's not even a physicist, okay? And this inference and quantum communication, So things like the capacity of sending information using quantum systems and so on, this was invented by 2 mathematicians, okay? So these people just took it and basically said, I don't care about what is reality, local realism, okay, what can we do with this thing, okay? And because these people did it, now we got $30 billion of funding, okay? And also, to my knowledge, this is the first time ever in the history of science where I know that the theorists are ahead of the experimentalists. We have a factoring algorithm. I have yet to see someone do an experiment that factors a number, aside from the number 15 and 21 that people did. But no one is building a device now that can factor a large number. Usually in history, it was the other way around. The experimentalists came up and say, hey, new phenomenon, we don't know this. And the theorists have to figure it out, okay?
Relativity is all theory until black holes were discovered.
That's true. Okay, I'll give you relativity. That one. Okay, but that one was very close. Huh? So it was only a short time. I mean, so Shor's factoring algorithm is now 20 years old. We still can't do it. So. Okay, so back to so now I'm going to use this abstract formalism. So the main ingredient in this abstract formalism is something called a qubit or a quantum bit, okay? You may think of a quantum bit as the fundamental unit of quantum information, okay? It's an abstract realization of the simplest quantum mechanical system you can have. Think, for example, of the spin of an electron, no? It can be up or down, or the polarization of a photon, which can be left or right, or, so, for example, an atom in a trap that can be left or right, okay? And it's also quite nice because there's a very nice mathematical picture of visualizing this qubit, okay? It's called the Bloch ball. Here it is. So things that are orthogonal are on opposite sides on this ball, okay? And on the surface of this ball, we have pure states, okay? States that can be parameterized like this, okay? If you want to think of density matrices, they can also be written like this, where this R is a real vector, a three-dimensional vector, whose magnitude is equal to 1, okay? And inside this sphere, you have something called mixed states, okay? States that correspond to ensembles of things. I know that the system is spin up with this probability or spin down with this other probability, okay? And these objects, the general way to classify them is to use this density matrix formalism. They also have a vector R, only this time the radius of this, the magnitude of this vector is less than 1, okay? Good, and that's it. This is everything you need to know. So here's a few realizations. It can be a spin-half system, like I said, spin up or spin down. It can be the way a photon goes through an interferometer. So for example, the blue is, I call it 1, and the red, I call it 0, okay? Or it could be an atom in a trap, okay? So say the atom on the left is 0 and the atom on the right is 1, okay? All these are different realizations of the same concept. And a lot of these quantum computing architectures that you read about, you hear, for example, about optical quantum computers. So optical quantum computers are essentially doing this thing, okay? Cold atoms, they do this thing, okay? It's different ways of realizing the same object, okay? Good. So now let me do a very, very simple experiment, okay? That hopefully most of you will recognize. And it's so simple that we are actually going to solve it all together right now, okay? So how many of you know what this is, or what this device is called? Somebody yell it out. No? Anybody heard of a Mach-Zehnder interferometer? No? No, come on. Okay. So this is a device called the Mach-Zehnder interferometer. Here, I'll tell you how it works, okay? So these dashed lines here are something called a 50-50 beam splitter. Physicists have a very nice way of describing things that are very literal. A beam splitter splits a beam. A 50-50 beam splitter splits the beam in half, okay? So if I shine light through here of intensity I0, say, half the light is going to get reflected and half of it is going to get transmitted, okay? Then these are two perfectly reflecting mirrors. And these things here are devices that are called photodetectors. They count photons. You get click, 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 okay? Okay, so now, this path, suppose that their lengths are such that the absolute value of their difference is an integral multiple of the wavelength of the light, okay? Which means that the light gets split here, and when the two waves arrive on this other beam splitter, they arrive in phase, okay? So the equivalent of constructive interference in this case is, well, if the light came in this way, and they come in phase here, it will exit this way. Likewise, if I put the light this way, and the waves come in phase here, it will exit that way, okay? Which means that if this is the path difference in the interferometer, what I do is all the intensity comes out here, which is here, and 0 there, okay? That's constructive interference. If, on the other hand, the difference is half a wavelength, then the waves will arrive here out of phase. They will destructively interfere, and now, instead of the light exiting this way, it will exit that way, okay? So I'm going to get, where is it? I'm going to get this, okay? And now you ask, well, okay, what happens if the path length is any other number? Well, if the phase of the waves is 0, all the intensity goes down. If the phase is pi over 2, all the light goes up. So if it's anything in between, you just get this relationship for the intensity, okay? And this theta is essentially this number here. It's related to the phase of the electromagnetic field, okay? And this is as good as it gets for a classical description. This explains the experiment if you think that light is a classical wave, okay? The question now becomes, what happens if I turn the intensity down so that a single photon is inside this device at any given point, okay? So imagine that I put the photon this way. Remember we said that photons that go this way, they have a state 1. So I put the photon here. What happens here? What is 50-50 beam splitter do? What happens is the light coherently splits into this superposition. The photon somehow simultaneously goes this way and this way, okay? And then the path difference being different simply implies that this, depending on which way the photon went, it will acquire a phase, okay? So if you can think of the entire device here as just implementing some unitary evolution or obeying a Schrödinger equation whose matrix representation is given by this thing here, okay? If I want to know what happens to the state of a photon entering here, I put this vector right here, I do matrix multiplication, and I get what the state of the photon is, just before the detectors click, okay? Now, the measurement that you do here is essentially the same as doing what's known as a Pauli sigma z measurement. You're measuring an observable. It's like asking the photon, are you up or down? And you put a +1 sign if the photon went up and a -1 sign if the photon went down, okay? And if you want to know what is the expected behavior of this photon, like what do I expect to see at the outcome, then all you need to do is to take the average of this observable with the initial state. And if you do this computation, you get that something which is called a cosine, something which is cosine theta, okay? So now if you want to remember, theta is related to the path length difference. So if you do this experiment, okay, and you get a value theta, you can invert this relationship and you get an estimate of the path length difference between these two arms, okay? And then since it's an experiment and you get an estimate, you need to give me an error. What is the error that you do? Well, if you do this estimate and you do the standard error propagation formula, the error you get is 1. So if you repeat this experiment n times, and each experiment is the same as the one before, and they're independent, what happens to your error? Well, you should know that your error goes down as 1 over n, right? The more times I do it, the smaller my error is. And this is indeed what happens, and this precision in the way that you estimate this path length difference is known as the standard quantum limit, okay? Given the number of photons you have, this procedure I told you for estimating the difference in the length of this path goes down as 1 over n, okay? Now let's do another thing, which is instead of sending each of the photons down the interferometer one at a time, suppose we prepare one of these states that Einstein had a problem with. So this state here, which is, again, physicists called a noon state, okay, is a state whereby I have n photons that simultaneously go up or down this path, okay? But all of them in an entangled way, okay? Now what happens now is the n photons that come down this way, each photon gets a phase e to the I theta, so the collective phase of this thing is e to the minus I n theta, okay? I get n times the phase, okay? And then if I go after the beam splitter, this is a simple computation. When you do quantum optics, everyone is going to do this. You're going to suffer. This is a standard thing that you do. The state is like this, okay? You see what the beam splitter does is you will recognize that this thing here is a binomial distribution, okay? So the beam splitter takes the photons and goes, it just sorts them, okay, into different modes. Okay, so what do you do now is you count photons again here, but this time you don't count how many. You're interested in whether or not the number of photons you hear is even or odd. So if I look here and I say, okay, the number I got, is it even or odd? If you do this measurement, and again, you do the expectation value, you say what I expect to see, you get something which is cosine n theta. And now you can extract an estimate from this one. And you can do your error propagation, and this time your error goes down as 1 over n squared, okay? Remember before when we sent them one at a time it was 1 over n, this time is 1 over n squared. This thing here is called the Heisenberg limit, okay? This is the most precise you can possibly get. Now, imagine that this interferometer now is, this arm is about 4 kilometers long, and this arm is about 4 kilometers long. And there's a station in the middle, right there. And the path length is because a gravitational wave comes in, and what the gravitational wave does is it stretches and compresses space-time. So if I build them exactly to be 4 kilometers, after the wave goes through, the length of these arms changes, which puts a phase on my photons, which are then, if I stand and measure, I see, if I didn't have any phase, for example, it's very easy to see that if I send this state, all I would get here is an even number of clicks. So I set up my interferometer. If it's perfect, the path length difference is 0. All I would see here is even numbers. Then a gravitational wave comes through, all of a sudden I see even and odd numbers. The number of times I see even and odd numbers I can use to extract information about this phase. This phase tells me something about the path difference, and this path difference tells me about the magnitude of the gravitational wave and its intensity and so on. And this is what we did and got the Nobel Prize in 2016. Okay? In fact, it's so astonishing. Here's the actual data that they recorded. Okay? Notice the number and the path length difference here is 10 to the minus 21 meters. The size of a nucleus of an atom is 10 to the minus 15. They measured a difference in path length which is a millionth of the size of an atom. Okay? That's why you get the Nobel Prize. And ever since they did this, there's an entire new field of research now called gravitational wave astronomy. They start building more of these interferometers, and guess what? Every time they turn them on, they see black holes everywhere now. There's gravitational waves everywhere now. Everyone is recording them now. So literally, the first paper was 2016, and almost every 2 other months, there's a paper going, oh, we detected another one. Oh, we detected another one. And it's everywhere, okay? Good. So this is what I mean, it's not a bug, it's a feature. Okay? So instead of worrying about what this state means, here, I used it to do something that even Einstein himself thought would be impossible. Nobody's going to ever detect gravitational waves. Well, we did it 100 years later. Okay? Now, let me switch a little bit of gears, and let me now tell you this was something which was very physical. So now let's do something which is more information theory. Okay? So how many of you, okay, this one, her name is already written here. So this is Hypatia. I think it's the earliest female scientist that I know of, and unfortunately met a very tragic, untimely death because of the Christians. I should point that out. And this is Claude Shannon, okay, the father of information theory. He really was a juggler, by the way, just so you know. Okay, so here's what happens now when we start thinking of quantum theory and start to do information processing with it. Okay, people started discovering a few very interesting things. You start to understand basically the formulation of the theory, and then you realize that you cannot copy quantum information. Also, you cannot broadcast quantum information. Also, you cannot delete quantum information. Also, you cannot add quantum bits. And finally, you cannot do unconditional bit commitment. Okay? By the way, this is a very famous game. It's called the game of the century. And as far as I know, bit commitment first appeared here because the two players that played each other. So just so I explain what bit commitment is. Suppose you play this game. It's late at night. It's Black's turn. Okay? And you have to go to sleep. And Black says, well, I don't want to play because if I play now, my opponent is going to go to his room. He's going to have a supercomputer. He's going to analyze all the possibilities, and tomorrow he's going to come and beat me. Okay? So I want White to play, and White goes, well, I don't want to play, because if I play, then Black is going to go to his room, and he's going to use his computer, and he's going to beat me, okay? So what do? The solution is you make Black commit to a move now. Basically, somebody says, okay, write down what you are going to play. And then I take this piece of paper, and then I put it in a safe, and I lock it, okay? And then the next morning, you play the move, and the referee opens the safe and says, okay, I verify he played the correct move. It turns out that there is no way, okay, that you can guarantee that this process, okay, will ever be safe. I could have a ninja that breaks in the night, breaks in the safe, looks at the move, okay? No other way in classical theory can do this, and it turns out you can't even do this in quantum theory, okay? There's no way to commit unconditionally. So surprising that you have all these things that you cannot do, and yet $30 billion to build a quantum computer. What the hell, right? Okay, so let me show you very quickly a very simple proof, how you can prove that you cannot clone quantum information, okay? So what you're looking for is, you ask yourself the following question: does there exist a machine such that for any quantum state I give it, it produces a copy of it, okay? So this machine is described by a unitary, okay, in the simplest version of it. And what it does is the following: it takes the state, this is whatever state you want, plus some state which you initialize in some fixed state, let's call it 0. And at the output, it's supposed to give me 2 copies of this state, okay? So if such a machine existed, mathematically, you describe it like this. And if instead of psi, I gave it another state phi, it's supposed to do this, right? But then what I do is I take the inner product of the left-hand side and the right-hand side. In the left-hand side, you notice that this here is the identity. 0 and 0 is 1, so I get the overlap of psi with phi. That's if I take the left-hand side here. If I take the right-hand side, I take that overlap squared. But this can only be equal if this number here is either 0 or 1. In other words, if the information you're using is classical. Otherwise, you cannot, okay? Simple, one-line proof, okay? Nature paper, 1983, just so you know. Okay, so then you ask, okay, not perfect copies, but can I do an approximate copying? Can I produce something which is close to what I want? It turns out that if you do this, then you can do it. What is an approximate copy? Is instead of asking for 2 perfect copies, you ask for an entangled state whose overlap with 2 perfect copies is very close to 1, okay? It turns out that this you can do. You can also do something which is, you say, okay, I don't want it for every state, but I want it for this set of states that are of interest to me, okay? So if you restrict the set, you can also do it, okay? And you can also do it in a probabilistic fashion, something that says, look, I want perfect copies, but the price I want to pay is that sometimes I fail, okay? Turns out that you can also do this, okay? Now, let me tell you how these machines work. The simplest way to copy something is to do the following. Give me many copies of what you want me to copy. I learn what it is, and then I prepare as many copies of it as you want, okay? And that's literally what the machines do. But remember, this is estimating. Learning something from many copies has this limit on it, okay? You cannot do better than this. How does a probabilistic machine work? A probabilistic machine does something which is a little bit crazy. Remember that noon state that gave me better precision? A probabilistic machine essentially does the following. Let me try and do a process called a filter, which converts the n copies you gave me into this entangled state, and then I use this state to estimate, which gives me a better estimate, and then I prepare, okay? It turns out that if you do this, what you can get is that the fidelity or the closeness of your copies will be something like this. Notice this n squared over m, which means that if you use this device, you will produce at most n squared very good copies, the price you pay is that this will only work a few times. Okay? The probability that you succeed in doing these copies will be very small. Okay? Good, that's for states. Then you can ask, okay, but if I look at this problem in a little bit of a different way, what I have is essentially the following thing. I have states which are on the equator, and I have rotations. The set of states you want me to copy are rotations about the z-axis, okay? So I can think of it like this, is you gave me n gates that do this rotation, and the protocol we just did before for states was input in every one of these boxes the state plus, which is the state that's on the equator, okay? But then I ask myself, okay, what happens if instead of this, I am allowed to put whatever state I want here, and I'm allowed to do whatever measurement I want here, and my goal now is not to copy the state, but to copy the entire gate, okay? What can I do then? Well, it turns out that you can do this, you can copy quantum gates deterministically, okay? Not probabilistically, with certainty, okay? And the way you do it is you exploit the following property. If you notice these states, here, let me go back. If you notice this, the states that we had here, if I take n copies of it, then I have a bit string, no? And this bit string has zeros and ones, okay? And the only thing that matters in this bit string is not where the ones are, but how many ones there are in this string, okay? I don't care about the location. So if you exploit this property, which is what we're doing here, okay? The same thing happens with the unitaries. The unitary adds an angle. If you remember in the interferometer, we said n photons, and they all get the same phase. I don't care the distribution of the photons, just that there are n of them, okay? So you can always write these unitaries in this very special way, which is this one here is m, as in how many numbers of ones do you have, and I don't care about the rest, okay? And then what you realize is that the distribution of bit strings, okay, follows a Gaussian. In other words, I have something, if I were to tell you pick from a bag, a random n-bit string, most likely this random n-bit string will be around the middle or around what's called the typical subspace, okay? Something which is plus or minus 1 sigma away from the middle. So your replication procedure, what you do now is you say, okay, I copy only those strings and I do random things for the rest, I don't care. It turns out that if you do that, then you can, with n uses of a quantum gate, you can produce another gate which is the same as if you use the gate n squared times. To put it in a way, I'm Greek, so for me the best way to understand this is, okay, IBM charges me 1,000 euros for every time I use a gate, okay? And I have 100,000 euros, so I can use a gate 100 times, but I want to use the gate 10,000 times, so I cheat, okay? And I cheat like this. I use their computer 100 times, but I make it look like I used it 10,000 times, okay? And in fact, if you don't believe me, this is something that we figured out with my colleagues in Innsbruck, and shortly after we published the paper, people actually did an experimental implementation using photons, and it works. They used the gate once, and they made it look like they used the gate twice, which is, I think, the only paper I ever wrote that had an experimental implementation ever, okay? Which is good. Now, you can do the same thing backwards. If instead of having n gates and producing n squared, I give you n squared gates and you compress them down to n. This is the same as when you compress files on your computer, okay? So it turns out that you can also compress quantum information. The question is, how well can you do it? Well, if your state is pure, it turns out that if you give me n copies of this pure state, I can compress it into a register which only uses log n qubits. If your state is mixed, all that happens is instead of 1 log n, I get 3/2 log n, okay? And the same thing happens for your gates. I can compress the dynamics of the system down to a smaller register. So this is very good if you want to do simulation, no? I want to simulate some chemical process, it's too big, okay? But it turns out that I can compress it into a smaller size that I can put in a quantum computer and I can simulate the process, okay? perfectly. Good. So let me see how far ahead am I? Okay. So the next thing is, okay, I can copy states, or rather, I can probabilistically copy states. I can deterministically copy unitary gates. What happens to the most general dynamics of a quantum system? So open quantum systems, things like, for example, systems that undergo spontaneous emission or spontaneous absorption, for example. Can I copy those? It turns out that you cannot do it for such systems, okay? The best you can do is get this 1 over n. There is no improvement here, okay? And this is recent work that we are doing recently, but so you cannot copy them. It turns out that you can compress them, at least slightly. And in fact, Danny and Pablo had actually done a similar process in one of their works when they were looking at these networks of systems with open system dynamics. Okay? If you actually read their paper, what they're doing is they're actually compressing the dynamics down. Okay? So it's already there. Good. That's all I wanted to say about, let's say, doing information theory in physics. Now I wanted to come back and put physics into information theory. So how many of you know who this person here is? This is the first ever computer scientist. Yes. Lady Byron, I think, is the official name. And this guy here is my favorite hero of all time. This is, because he has the best name, is E.T. Jaynes, of the Jaynes-Cummings Hamiltonian, okay? This is the first guy ever that I know that used information theory to derive all of statistical mechanics, okay? If you ever heard of a thing called the principle of maximum entropy, well, it's this guy, okay? Good. So, when we do information theory, at the end, what we're doing is we're sending to each other physical systems. So, at the end, we're bound by physical laws, okay? And now there's two types of information. The first type of information is what's known as a speakable information. What I've been doing for the last hour, okay? So, for example, I can tell you my name by pronouncing it. It's con J, by the way, Michalis, okay? Or I can write it, or I can send it up in smoke signals, or I can do it in Morse code. There are several ways I can communicate this information to you. That's why it's called speakable, okay? But then there's information which I cannot communicate to you in any other way other than sending you a system. For example, things like time. If I wanted to compare my second to your second, there's no way I can call you and tell you, well, my second is ticking. No, okay? I have to send you a clock. I have to send you a pendulum that says, here's my clock. Here's how it's ticking, okay? The same thing with my rulers. The same thing with my, for example, point your camera up. Okay, which way is up? Okay? These things, you have to send me a system to tell me information about them, okay? And they're called unspeakable information. So, here's an example just so you understand it. Imagine I have two parties, traditionally called Alice and Bob, okay? And Alice wants to send a message to Bob. Actually, she wants to send him a classical message, a 0 or a 1, okay? And what Alice does is she uses a spin half particle, say an electron, okay? So she prepares an electron and she prepares it in one of these two states. 0 is plus, 1 is minus. The important thing to note here is that these two states are orthogonal, which means they are perfectly distinguishable. So she can communicate this perfectly, okay? So what Alice does is prepares the system in either plus or minus. She sends it over to Bob. Okay, assume that she sends it in a way that is noiseless. It's perfect, okay? And then Bob makes a measurement and tries to read the message. So in this case, Bob will take a Stern-Gerlach magnet. He will point it in the x direction. If the system goes up, he knows that Alice sends him 0. If the system goes the other way, he knows Alice sends him 1, okay? But this communication scenario only makes sense if Alice and Bob both know what x direction means, okay? So if they both know this is up and this is x and this is y. Imagine that Alice and Bob have different notions of orientation, okay? And moreover, both know the relative orientation of his frame to Alice's. So for Bob, x is this one, and he doesn't know what x is for Alice. Well, in that case, you have to average over all possible orientations. And in that case, if you do this for the systems that Alice is sending, Bob gets no information, okay? So if you do not share a common frame of reference, there is no way of communicating. Imagine doing the same thing, for example, with an alien that lives in a universe where parity is reversed, and you try to explain to the alien that my heart is on the left side. Good luck. Okay? Good. So what can Alice and Bob do then to rectify this? Well, they can do one of two things. The first one is they say, okay, hold on, okay. I send you a gyroscope that points in my x direction. I will send it to you, you can take it, and then point your magnet in that direction, then we can communicate, okay? Now, a gyroscope is a classical system. Imagine that Alice only has spins, so she has to send Bob spins, okay? So let's do a simple example. Imagine that Alice wants to send her x direction to Bob, and the only thing she can do is she can send him 2 spin half systems. And the question is, in which state should Alice prepare her spin half systems such that Bob has the largest probability of correctly identifying Alice's state? Take a guess. For example, does it make sense for Alice to prepare the system pointing in the z direction? No. So she might as well point them at x. The question is, does she point both the spins in x? You say no. Why? What does she do? You don't know. Okay, it turns out that the optimal thing for Alice to do is to actually send the first spin pointing along x and the second spin pointing the opposite way, okay? And there's a very easy way to understand why this is the optimal thing, because if you look at these 2 states, they are permutationally symmetric, right? Which means that if I apply the same unitary to them, they span the triplet space, which is a 3-dimensional space, right? Whereas if I send them anti-parallel, then they span the whole 4-dimensional space. So 4 dimensions means there's more space, means things are more distinguishable, which means Bob has more chance of actually estimating the direction, okay? So this is what Alice needs to do, which was a surprise. It turns out that actually this can be generalized. So if Alice had n spins, what she needs to do is to prepare them in this, notice, massively entangled state across systems that have different values of total angular momentum, okay? And what Bob needs to do is something even more spectacular, because Bob has to do a measurement which is unlike any measurement you will ever see in your classical quantum mechanics course. This is called the positive operator value measure. It's a continuous measurement, okay, that Bob has to do. And if they do this, they can be shown that the probability that Bob guesses correctly, or that Bob estimates Alice's direction with a precision that goes as some constant over n squared. Remember this one? This is the Heisenberg limit, right? Whereas if Alice just sent the spins individually, the precision would be something over n, okay? Good. Now, the thing is, okay, identifying what systems to send and in which state to send them such that you have the best chance of aligning your reference frame is an entire field of research. It's in fact so important that we had to go out and identify these systems, which are called tokens of reference frame, okay, for every different symmetry. For example, if what you are lacking is a clock, in other words, the phase, then what you need to send is an optical signal that is a superposition over different numbers of photons, okay, with some probability. The value of this probability depends on how you quantify your success. But for example, this explains why lasers are good phase references, okay? Lasers are exactly like this, and this probability distribution here is a Poissonian, okay? It turns out that you can do this, you can build an entire resource theory where you can unambiguously rank the states of physical systems from this is very good to this is very bad, okay? And in fact, in resource theory, it can be used to study what are the key properties that quantum systems have to have in order to be able to compute things better, estimate things better, okay? Is it the entanglement? Is it coherence? Is it asymmetry? What is it? And this entire field goes by the field of resource theories, okay? It's something that's very, very useful to do. Okay, now let me go to the last part. This is the last thing I'll do, and this is the one where I put physics back into the game. So you may have noticed throughout this talk that I said things like the precision is 1 over n squared, the replication rate is n squared. Okay? Where does this n squared come from? Well, in all honesty, everything I showed you so far, it comes from a brutal mathematical optimization. You literally sit down, you are given a function, optimize it, okay? And you optimize and you get this number, okay? But if you're a physicist, which deep down I am, you want to know, okay, but there must be some other reason why it's n squared. Why not n to the whatever power, okay? Is there a physical constraint that tells me that this is the best you can do, okay? So we, with my collaborators in Innsbruck, went out and said, okay, let's try and see if there is a way that we can figure this out. And turns out that there is a way you can figure it out, and it has to do with a problem that was first noticed back in the 70s. Okay? It has to do with superluminal communication. Imagine that you have two parties, Alice and Bob are space-like separated, okay? But for the moment, imagine that Alice and Bob, they share this maximally entangled state. You may recognize this state as a Bell state. This is the one that people use to demonstrate the violation of a Bell inequality, okay? So here's how a communication scenario operates. Alice makes a measurement. She can decide to measure either along the z direction or along the x direction, okay? If Alice gets, whatever outcome Alice gets in that measurement, Bob's outcome will be the opposite, right? So if Alice measures sigma z and she gets 0, she knows Bob's is 1. If she gets 1, she knows Bob's is 0, and likewise for the x, okay? Now imagine that Bob could perfectly clone his part of the state, perfectly, okay? Then what I'm about to show you is that if this was possible, then Alice and Bob can do superluminal signaling. And here's how it works. Bob can produce as many copies of his system as he wants. He produces, I don't know, 1 billion trillion of them. He can estimate what the state is, so he can learn what is the state of his system way before any message from Alice arrives telling him, I did this measurement and I got this outcome, okay? So you cannot clone, because if you could, you put a signal faster than the speed of light, and Einstein wouldn't like that, okay? Now, this explains why you cannot clone, but it doesn't explain why the best you can do at cloning is 1 over n squared. So to explain that, you have to delve a little bit deeper here. And you say, okay, instead of the maximally entangled state, let's just do the state cloning now, okay? So imagine that Alice and Bob, they share a particular entangled state. Now, I've engineered this state for the purposes of this discussion, okay? But it's part of the problem. They share this particular state, okay? And what happens now is Alice remotely prepares Bob's system. How does she do that? Alice performs the gate, okay, n times on her system, and then she makes a measurement in what's known as the Fourier basis, okay, the conjugate basis to this n basis. And she gets an outcome, okay? If Alice does this, then by what I told you before, Bob, if Alice's outcome is k, then you are guaranteed that Bob's state will be of this form, okay? But since Bob doesn't know Alice's outcome, then what Bob describes is this one here. Now, the no signaling condition basically says the following. Whatever Bob does to this state, it has to be independent of theta. It cannot depend on theta, okay? So, for example, if Bob wants to use this state to produce m copies, whatever he does has to be independent of theta. Notice that whatever he does not pertain to quantum mechanics. I am allowing Bob here to do whatever he wants, even theories that we haven't even invented yet, so long as they respect the no signaling condition. And if you do this, you can prove that the worst case overlap in any such scenario is this one here, and this goes to 1 if m is at most n squared. And you can do the same for the gates. Okay, you can get the same limit, and most importantly, you can get the same limit for any estimation protocol. Think about this. The precision with which you can measure things in your lab has to do with the fact that the universe you live in has a finite speed limit. That's messed up. Okay? It doesn't matter what the speed is, as long as the speed limit exists, there is a bound on how well you can estimate things. Okay? In fact, what we proved in this paper is that no theory, even the one that supersedes quantum theory, would ever be able to do this task better that one you can do quantum mechanically. Okay? It is impossible, unless you prove to me that no signaling doesn't hold in this universe. Okay? And that's it. So in the last minute, I'd just like to say that I'm the new member of the Quantum Information and Thermodynamics group, which consists of 4 people, which you may know. This is Dani Manzano and Juani Bermejo Vega and Alvaro, who's sitting here. See, I didn't use the bad picture. I used the good one. Okay, good. And I just want to put up the kind of things that we're working on. Okay, this may not look they might be very mysterious to you, but if you want to know more, we are in the Electromagnetism and Statistical Physics group. Come knock on our door. We'll be happy to tell you. Okay. And I also like to say that every other Friday, so for example next Friday, we have a group of seminars where we go through most of this quantum stuff that I told you about. Okay. If you want to learn more specifically how to get to these limits, if you want to join, please send an email to me. Oops, here, and that's it. Thank you very much. If you want, you can ask them in Spanish. I can get a translation, I guess. No? Yes. Yeah.
Where does quantum complexity go in that case? You were mentioning our work.
Yeah.
In that case, we were able to compress information because there was some symmetry in the system. So in that case, we could do it. But in general, I wasn't so sure.
In most of these compression algorithms, you can compress because you have n copies, right? So automatically you have permutation symmetry. Things like this. So the fact that you have this symmetry already is present. That's entirely the reason why you can do it. Yeah. Everyone's too shy.
I'm a second-year student, and I really don't have any idea about quantum physics or quantum theory.
You're a first-year student, you said?
No, second-year.
Second-year student, okay.
And I found really interesting the last thing you explained about how atoms are supposed to communicate. Do you think you could sum it up with a bit of with simple terms so I can understand it a little?
Okay, so how do you communicate? So when you pick up your phone now and you call someone, how does that communication work? Well, your phone sends a signal that gets received by an antenna, that gets sent another signal, and all this is encoded either in the frequency of the wave or the amplitude, okay, or both. If you do quantum mechanical communication, what you would do instead is you would send a quantum system, so a photon down an optical fiber or a photon into free space and so on, okay? And what you would do is you would encode it either in the polarization of the photon or some other property, or the angular momentum of it or something like that, okay? And the idea is, okay, how much information can I put in a quantum system that I can reliably transmit to another person, okay? It turns out that if you use classical systems, so if you encode classically, this capacity is some number. If you use quantum systems, this capacity doubles, okay? In some cases, it even triples. In fact, you get a property that in some cases, this capacity, the more systems you have, it amplifies. Okay, so if you have 2 systems instead of twice the capacity, you can get it 4 times, 6 times, 8 times. Okay, so this is why people are using these things. Okay, you can squeeze more information into the same number of resources. That's the idea. Okay.
I am a third-year student, and in third year we have our first quantum physics course.
Okay.
And to me, it's really weird the idea of information, and I think I don't really understand it.
Okay.
Give me my information.
So information is okay. So you're a physics student, right?
Yes.
So when you do quantum physics, what normally, I guess, if it's the same as in Barcelona, what will happen is you will learn about black body radiation and the ultraviolet catastrophe, and then harmonic oscillators and all this. Okay. Information theory is people go and say they look. So you will learn the axioms of quantum theory as I wrote them the first time, wave functions and all these things. information theorists take it and say, okay, no, what exists is these Hilbert spaces. I have vectors, okay, and these vectors, I can use them to encode information, okay? And then there are rules about how to manipulate this information, okay? And then this is, you say, okay, what can I do cryptography with this? Can I do computation with this, okay? That's the idea. Now, the problem is that these are two different edges, right? So the information theorists, they don't know about physics. They don't know the fact that, well, I cannot do what you're saying, I cannot do this continuous measurement. You go to an experimentalist, goes, well, you must be joking. No, I cannot do this thing, okay? And on the other hand, the physicists also don't know about these information theories that do all this, okay? The nice thing is that somewhere in the middle, you have to come somewhere in the middle and say, okay, guys, we can do information processing, but there are these limitations. Can you tell us what can we do with these limitations? Okay? So this is the idea here.
Information theory is not then like a physical theories or like a mathematical.
Yes, but you do it with physical systems, no? So that's the idea. That's why I'm saying it's somewhere in the middle, no? That's the idea.
So any other question? No?
So let me play the devil's advocate, if you don't mind.
Cool.
I really enjoyed your talk.
Yes.
And if I understand, this attitude is, okay, let's not bother about what happens in the double slit, whether the electron goes through one or the Mach sender. Let's not bother about the EPR paradox because it just works.
Mm-hmm.
It does work. It's working.
Yep.
That's what you're saying. And
Yep.
it's true. And yet, I, as a physicist, I'm two things. I'm bothered, and I'm also, I think that we as physicists still need to think what does happen to the electron in a double slit. Is it really both a wave and a particle? What does happen with the EPR paradox? Does entanglement really mean that a particle kilometers away is reacting
To
an
a particle.
And I do think that somebody, somewhere in this universe, in this world, is going to come up with a theory that explains better to me what happens in the double slit apparatus, or better what happens when I entangle two particles.
That's true.
It is mind-boggling if you actually think about it. Not the mathematics. The mathematics works, yeah, and the mathematics has physical consequences, but the physics didn't make sense for Einstein. That's why he called it spooky action at a distance, and it doesn't make sense to me, and I don't think it makes sense.
That's
to any of us.
as far as I know, it doesn't make sense still.
Right.
Okay.
It
Yeah.
makes sense mathematically, but not physically.
Hold on.
I can answer this as a physicist.
Okay.
The electron is a particle, but this is a mystery. Electron is a quantum of a field.
Yeah.
A field is an extended object. An extended object can go through both slits, at the same time. So
Yes.
this is the object, the physical object we are talking about.
Yes,
It's not a particle. It's a field. The field is extended. It can move through slits. It can interfere. Of course, you can describe the whole thing with vectors in a simple space.
Mhm.
Each analogous is completely equivalent. But if you want to know the physics, if you want to have some physics behind, my only answer to this question that I made myself very, very long time
It's field theory. Yes.
is a quantum theory.
This is absolutely true, but then so are we, because there's no cutoff, and so this is the problem. You make a double slit, you can now send big organic molecules in double slits.
Sure.
Correct.
And at some point you could actually send me for a double slit.
Yeah, we are made
No,
of
I think they have proof and limit. I think Marcus is working in quantum.
Actually, I have a limit on that too. Yes. We also have a limit from physical principles how large things can be. Yeah, but that's true. Now it's an experimental one. Okay.
Joking about sending me.
There is another. There is another. So there's an entire thing I forgot to mention simply because I didn't want to get into this discussion. But since you brought it up, then let's do it. So the other consequence of information theories. Okay, but then let me tell you. Which is my favorite. So there's all these interpretations of quantum mechanics. People trying to figure out exactly how to explain quantum mechanics. Okay. The other nice thing that happened with mathematicians and information theory into this field is that they started looking at information theoretic axioms for quantum mechanics. In other words, you're not going to get something like relativity, which says the speed of light is constant and every observer is equal. What if we actually said that The rules of the universe is that you cannot clone better than this, you cannot copy better than this, you cannot broadcast, and you cannot do unconditional bit commitment. How much of quantum theory can I retrieve if I just assume that the physical principles are information theoretic or information processing? In other words, I treat the universe as a computer. Okay? Maybe that's the reason. And indeed, people have gone quite far. There's a very famous paper by Bubb and Halverson, which I called Information Theoretic Principles for Quantum Mechanics. And they only use 3. They say no cloning, no broadcasting, no unconditional bit commitment. Okay? And they can explain everything, but there's one trick to it. They have to assume a Hilbert space. So they, okay, but you have to explain where the Hilbert space comes from. But with these 3 principles, you can explain almost everything. Okay? So there's this idea behind it, which I don't know, for physicists is more like, oh, but okay, you can do this. Okay. The theory part, okay.
But if I understood it correctly, I think that you are limited in the amount of perfect copies and you can make a system and all that stuff. So my question is how that can limit the precision that we can achieve with quantum computers.
How do you limit it?
Yeah, like if we are like every year quantum computers are being developed with more and more qubits.
Yes.
But as you said, there's like this limit.
So the limit in estimation, I've already assumed the best thing possible. Okay. So it doesn't matter how good your quantum computer is, it will never ever be able to get better than this 1/n squared. Okay. In fact, what we showed is that it's not even a quantum computer thing. It's if you give me a theory that's even better, that supersedes quantum mechanics, it too will not be able to do better than this. Okay? That's the idea. So,
As we develop more better and better quantum computers, we are closer to that limit.
correct. So for example, the LIGO interferometer is a quantum device. You detect the gravitational waves because you could get the noise down so low that you can see this path length of a millionth of an atom. Okay, there's countless more examples. We can estimate magnetic fields that are of the order of nanotesla using quantum systems. We can estimate like phase differences that are very small. We can do spectroscopy that's very small. We can distinguish point sources beyond the Rayleigh limit now because we have quantum devices. I mean, you can do a lot of spectacular things. Okay.
Okay, so it's Friday. We should leave now. Thank you very much.
Thank you.